Moving along in our discussion of sets, we're going to start to look at relationships between two sets. We're going to talk about a subset, which is a specific relationship. We say that A is a subset of B if every element in A is also an element of B. Logically, we would say for all x, if x is an element of A, then x is an element of B. Notationally, the symbol for subset is a sideways U with a line under it. Now that's very similar to sort of the less than or equal to sign, and you can sort of see the connection here. Saying that A is a subset of B is really saying that A is some part or all of B. Okay, now we're not just talking about number of elements, but there is a relationship there between those sets. As we start to do more with sets, we're going to introduce a visual representation of sets called Venn diagrams. We use a box around the outside to represent a universe, right, within which all of the possible elements of sets could belong to. And then sets are represented by circles. We draw a circle and label that circle with the letter that represents it. So this is the circle B. And if we want to represent A is a subset of B, then what we would have to do is draw the circle A arbitrarily inside of B. Now, with Venn diagrams, the size of the circle does not really matter. Even the fact that there's a space between A and B really just allows for there to be elements out here that are in B but not in A, but it's also possible that they're empty. So when we draw a Venn diagram, we try to think of the most general situation, but understand that any part of this set could be empty. Now sometimes when we introduce Venn diagrams, just to make sure we all understand them, we'll put a few dots here. So this particular dot here, right, this is an element. If we call this thing x, x would be in A, and x would also be in B. Okay? But if we think about an element out here called y, right, that element y is not in A, and y is in B. And if we take it one step even further to look at an element outside of here called z, right, z would not be in A, and also z would not be in B. Okay? Now, for any given sets A and B, it might be the case that there are no elements that are in A but not in B. There may also not be any elements that are in B but not in A. So when we draw this general Venn diagram, it doesn't automatically assume that each of these regions described are non-empty. That depends on the set itself. Now, one situation we know that all squares are rectangles, right, but not necessarily the other way around. So we could sort of represent a Venn diagram to think about all the sets of rectangles here and recognize that squares are part of them. But we couldn't do it the other way around. And if you notice, there is a sort of non-symmetry here to this symbol. If we just flip it around, it doesn't always work. So just because A is a subset of B rarely means B is a subset of A. It certainly doesn't automatically, and rarely would it be the case. There is, in fact, only one case where that would happen, is if A and B were exactly the same. Okay? So we can describe relationships between sets. We can determine whether or not one set is a subset of another. Right? But there's also a couple important properties. By default, the null set is a subset of every S, any set S. Okay? It might be a little bit hard to understand, but if you go back to the logical definition here, if x is in A, that's the one on the left, then x is in B. We have an implication here. The null set is the null set in A. Well, the null set's not in anything. So if the first part of this implication becomes false, then by default, the implication is true, because false implies false and false implies true. So this is sort of has to follow based on our logical definition of a subset. But you could always think about a subset as a group. Right? Think about a set B, and you decided to pull some of B out. Well, it's possible that you pulled nothing out of B. So one group you could choose from the larger set S would be the empty set, the set of nothing. On the other hand, you could also choose all of S to pull out. So S is always a subset of itself. Now, there is a symbol in the book called the proper subset, where we would draw A subset of B. Right, this looks a little bit more like a U sideways than a C, without the line underneath it. And that's sort of the equivalent of how the not less than or equal to compares to the less than. You can only use the proper subset when A does not equal B. Right? So you're saying that A is some portion of B, but it is not all of B. Okay? We're not going to spend a lot of time on the proper subset. If you get into a math course dealing with sets, you'll probably spend more time on that. Here's a more typical example of what you would be asked to do as a subset problem. So here are three sets. A equals the elements 1, 2, and 4. B is 1, 2, 3, 4, and 5. And C is 1, 4, 5, and 8. One simple question you might be asked, and you'd probably be asked to explain this, is A a subset of B? Okay. Well, in order for A to be a subset of B, for everything in A, it also has to show up in B. So the number 1 in A shows up in B. The number 2 also shows up in B. Right? And the number 4 also shows up in B. So we can say yes. Everything, every element in A is also in B. Okay? Now, if we decide to do the same thing for A being a subset of C, let's just clear these out. Right? We start with the number 1. The number 1 is in C. When we get to the number 2, we don't see 2 anywhere in C. So we can say no, because 2 is in A, but 2 is not in C. Okay? So if you're going to answer yes or no for a subset, you should give some sort of justification. This would be sufficient. Okay? One of the applications of subsets is we can talk about the power set. And the power set of a given set is all of the subsets of A. And I put here a little note that includes all or none. Now we designate the power set using an uppercase P. There's sort of a script-looking P, but we'll just write it as a regular P. Here would be an example. So suppose you have the set A, B, and C. The power set of A is all of the subsets of this set. That means any possible grouping you could choose of the elements of A. Okay? Now, I'm also going to ask you for the cardinality of A, of the power set of A, but we can't really answer this second part until we have this first part, until we figure out if there's a formula to generate this. Okay. Now, we could just sit here arbitrarily and write out portions of A, but we could also be systematic about it. Okay? We could take none, we could take 1, we could take 2, or we could take 3 elements from A. Those are the only possible subsets of A. The set of none would just be the empty set. Now, how many sets of size 1 could you choose from the uppercase set A? You could choose just the element A, just the element C, B, or just the element C. And then if you're going to choose sets of size 2, maybe you want to pick 2 elements from A. Well, you could choose A and B. You could choose A and C. Now, you can't choose B and A because A and B and A are the same. So the only other choice would be to choose B and C. And there's only one way to choose all 3. Right? So we'd say the power set of A is actually a set that has in it all of these sets. Okay? Now, I'd probably be okay if you just showed me the work above. Don't necessarily have to write this out again. You're really just copying down the work you already did in a more systematic and organized fashion. Right? But if we count these up, there's 1, 2, 3, 4, 5, 6, 7, 8. The power set of A has a cardinality of 8 when the cardinality of A is 3. Okay? Now, there turns out to be a nice formula to predict the cardinality of the power set of A. And if you know how many elements are in the power set, it'll make it easier to calculate. So let's take a look at a few examples. Okay? if we look at the cardinality of A and the cardinality of P of A, I'm going to give you a few examples and see if we can look at and describe the pattern. Now, I'm not going to take the time to work all of these out, but if your set A is the empty set, right, then you only have one element in your power set, and that's to choose the empty set. If you have one element in A, then you could either choose it or not choose it. That would give you 2. If you have 2 elements in A, right, there's going to turn out to be 4 different elements in the power set. We just did 3 is 8, and you might start to see a pattern here. Okay. If you wanted to count this down to a general n, it turns out that 1 is really 2 to the 0, 2 is really 2 to the first, 4 is really 2 squared, 8 is really 2 cubed. So the cardinality of the power set of A is always going to be 2 to the n. And that's because for each element in A, you can either choose to have it or not. That's 2 choices for each. When we get into counting techniques later, you'll see that this is an example of the multiplication rule counting technique. Okay? So why does this even matter? Why do we care about power sets other than to just make up a nice math problem? Well, here's an example of where you might do something like this or use something like this. So suppose we have a pizza place that has 10 toppings, and you can add either none, some, or all of them to a pizza. How many different sets of toppings could you order? Okay. Now, we don't want to start writing these out because there's going to be 10 choices for just one. Then if you have to choose 2, it's going to get really out of hand very quickly. We're just asking how many different sets there are. Well, we basically told you that there's a set of toppings. The cardinality of that set of toppings is A. Now I'm using A for the set of toppings. Maybe I should have used T, but we'll just stick with it here. So then what's the cardinality of the power set of A? Well, it would just be 2 to the 10, which would be 1,024. And that's the number of different ways you could order a pizza if you could choose up to 10 toppings. Okay? So if you imagined there were 10 toppings and we labeled them 1 through 10, you could choose the 1st, the 3rd, the 5th, and the 7th, or you could choose the 2nd, the 4th, the 8th, or you could just choose the 9th, or you could just choose the 10th, or you could choose none of them. If you decided to take the time to write those all out, you would get 1,024 different pizzas. Okay? So that's one use of the power set. We'll come back to this idea of counting techniques later in the course.